Hello and welcome to my video. Let me see if I got my little monitor up here. So in the background I got the Pythagoras statue. I think that might be in Somos where he's from. It's kind of a cool statue. So anyway, today's problem is all about finding the missing area, or finding where the extra area comes from. So in the problem that I presented here, and I got this from my high school math teacher, and I'm not sure where he's found it, but that's a problem I've seen many places. My favorite high school math teacher, I should say. Anyway, puzzle number 2 is called draw a straight line from the top to the bottom of the square, passing through its center of the square. Then draw a line from the left side to the right side of the square, intersecting at right angles. So following that instruction, if I were to take and let's say draw a line from, let's say, here to here, try and get it to go right through that center, and I'm going to have to adjust mine because my computer does some weird stuff with it. And then I need to get a right angle, so I'll use a protractor at this point, although I prefer using compass and straight edge. And I'm going to turn this so that it's right at 90 degrees. And for right now, since I have the ability, I'm going to draw a straight line along that edge. And then I'm going to adjust that straight line. So let me move this out of the way here. And I'm going to put this right through there. So if I've done this well, I'm going to end up with 4 pieces. Piece 1, piece 2, piece 3, piece 4. And these 4 pieces are going to be cut out, and then with the cutouts, I'm going to take them and rotate them all 180 degrees. And when you do so, you end up with these 2 pictures. So let's say I cut out these 4 pieces here. Now these 4 pieces, they form the total area of the square, but when I take those 4 pieces and I rotate them each 180 degrees, so I'm going to take and I'm going to go ahead and put here, if I rotate this 180, doesn't matter which way, and this one 180 degrees, and this one 180, and this one 180, and I connect them as so, I end up with a big hole in the middle. Then the question comes, after you've done your rotation, now cut out the 4 sections and construct the one at the right. Great, where did the hole come from? Well, so I've done a little bit of thinking about this, and here's what I come up with. In this picture here, if you rotate, I'll call this side X and I'll call this side Y. If you rotate these pieces 180, that puts X up here. And when you rotate this 180, it puts Y right here, right? So, and actually, if we look at this even more carefully, since these 2 diagonals, they intersect each other and they cut these into congruent pieces. This piece is congruent to this piece. These could both be labeled X. And we'll do that in a little bit, or look at that. But if you look at this piece, which is bigger than X, we'll call this X prime, and we'll call this Y prime. This is smaller than X. When you rotate that around, you end up with X prime here, you end up with Y prime there. Now, not the best notations, but you're getting the idea. So this length, and I'm going to kind of try and make this as obvious as possible now. The distance from here to here is the same as the distance from here to here. So where did the extra area come from? Well, I contend that it came from the fact that this distance is longer than this distance. So the distance from here to here and the distance from here to here are not congruent, and that inaccuracy, that extra this extra length, is going to create the area in the middle. The question is how much longer is it actually? So what we're going to do is we're going to look at this from the perspective of this picture right here. I noticed that if I were to take and rotate the original, let's say I were to cut this vertically and horizontally, and the distance from here to here, we'll just call that B. So if we call that distance B from here to here, and this distance is B, so this must be have an area of B to the second power, B squared. So now if I take this piece right here and I rotate it, as I'm rotating it, this length is getting longer. Now, it may not seem like it's getting longer, but it is getting longer, and here's some proof for that. If I were to take and draw a horizontal line from here to here, which is parallel to the B at the base, then I know that the length of this horizontal line here must be B. And I formed a right angle here, which means that this diagonal, which is now the hypotenuse of a right triangle, has to be longer than B, and B is a leg. So if I call this B and the unknown distance from here to here, let's call that A, then logically, let's call this distance from here to here, we'll call it C. So I have a regular Pythagorean right triangle. Leg squared plus leg squared equals hypotenuse squared. The hypotenuse is longer than this value at B. Now, the more I turn it, the longer it's going to get, up until the point where I'm going from corner to corner on the square. But right now, I can see that this is definitely longer. So, keeping that in mind, if this is B and this is B, here's A, here's C, then the new square, in fact, we can go back a couple pages here. So that means that this must be a C by C squared, and this must be a B by B squared. So this middle part, this extra part, that's our unknown. We want to find out how much, what the area of that part is. So I figured that if this is 1/4, whoa, that's not a good color. If this is 1/4 of the original B squared, and this is 1/4 of B squared, and this is 1/4 of B squared, and this is 1/4 of B squared, then that means that these four pieces here must also be the B squared. So here's my 1/4 of B squared, 1/4 of B squared, 1/4 of B squared, and 1/4 of B squared. So I know right now that the value for the missing part must be whatever's left over from C squared. So then I started thinking about if the value of this box comes from this distance, okay, so let me get back to what I was trying to do here. So if the diagonal length, which we now are calling C, and this part is A, and this part is B, if we have our right triangle here, I want to know what the length of C is, because I want to know what the exact area is, but I want that length of C in terms of A and B. So I know that A squared plus B squared equals C squared, which means that C must be the square root of A squared plus B squared. So if I replace that value over here, C is the square root of A squared plus B squared, square root of A squared plus B squared, then I know that the area of the new square, so the area of the new square is going to be C squared, which will also be the square root of A squared plus B squared squared, or the area will just be a squared plus b squared, which means that the missing piece, if these quarter 1/4 b squareds add up to b squared, then this missing piece has to be the a squared. So I now know, that this missing piece is a squared, which is kind of cool because that means that a squared plus b squared, the a squared plus the b squared equals the c squared. And there is the Pythagorean theorem hiding in that missing area. You gotta love it. For a cleaner picture, here you go. So if we took this and rotated that side so that c is this new length, we have a c by c squared. Each of these pieces, which are congruent, are going to be a quarter of the original b squared. There's 1, 2, 3, 4 of them. And the missing part is the a squared. And you can actually see, which is kind of cool, that the length from here to here is actually the same length. If I were to take this piece and turn it, you can see that it fits perfectly. It's the same length as the square that's inside. It's a very cool idea. I like it. Thank you for listening.